Hello. We are going to be looking at 6.3, the first part of 6.3 today. And we're going to kind of teach you something new. And it is this thing called logarithms. And if you're anything like me, you have no rhythm. But hopefully by the end of today, you will all have some logarithm. And that is my horrible attempt at humor to try to get you excited about what logarithms are, if that is even possible. But basically, what a logarithm is the logarithm is the inverse of an exponential. So let's kind of put this in the context that you're used to. Inverses, algebraically, if you have addition, to undo addition, you need subtraction. You can't solve anything with addition if you don't have subtraction, because those are inverses of each other. Similar, if you have a times 3 and you're trying to undo multiply by 3, then you'll divide by 3. So we've already looked at exponentials. We do have exponentials, exponential growth. So if we have exponentials, what that must mean is that we have the inverse of exponentials, and the inverse of exponentials is what we call logs for short, logarithms for lengthy vocabulary here. And I will just say, the sooner you understand the concept I'm about to write down right here, the sooner you understand this, the better off you are going to be. Okay? This idea that I'm about to write down is paramount. So, like I said, please make sure that throughout this entire video session here, I'm going to keep coming back to this. So the sooner you understand this idea, the better off you're going to be. So I'm actually going to write two equivalent statements. One has this log in it. Every log will have a base, so that's why this little lowercase b, it's not an exponent up here, it's actually like a subscript down here, b. So log base b of y equals x. That's how you read that. Log base b of y is equal to x. That is an equivalent statement to taking the base to the power of x, and that will equal y. When we talk about exponents, we should be familiar with this idea as the base. This is the base still, b. To the power of x, your exponent is equal to y. These are interchangeable, equivalent statements. You take the base, you cross the street, raise it to the power of x, set it equal to what's next to. All right? So the sooner you can understand log form, exponential form, and being able to go back and forth between the two, the better off you're going to be for the rest of this unit, because a lot of what we do from here on out is going to utilize this fact. Okay, so we'll practice it just kind of in general here, going from one form to the other. All right, so let's take a look at these examples down here. Log base 4 of 16 is equal to 2. So my base is 4. I'm trying to write it in exponential form. So if my base is 4, cross the street, raise it to the power of 2 equals what's next to. And is that true? 4 squared equals 16? Yes, that is true. So base to the power of what's over here equals what's next to. And 4 squared does indeed equal 16. So let's take a look at this one here. Base to the power of what's over here equals what's next to. 3 to the power of negative 2 is equal to 1/9. Is that true? Well, yes, negative exponents means 1 over 3 to the positive 2, and 3 to the positive 2 is 1/9. So that is accurate. Okay. Notice neither one of these have logs in it, but these are equivalent statements. Okay. So this is exponential, this is logs. They are inverses of each other, but this relationship of base to the power of what's over here equals what's next to is going to be really, really important for us. Okay. So once again, since it is so important, I'm going to rewrite it up here again. So you can do these U tries right here. And then you can check on Google Classroom. There is a answer key posted for these notes, and hopefully you can do those successfully. All right. So those were when we were in log form and we rewrote it to be an exponential form. Now we actually have exponential form and we're going to rewrite it in log form. So what we have here is this is now my b to the x is equal to y, and now I'm rewriting it in this form. So my base is 6, so the base of my log will be 6. And what we did is we raised it to the power of x. In this case, this is to the power of 3. Notice the power, the exponent, the x is over here. Other than the number next to, that's like my y. So what this needs to be is log base 6 of 216 is equal to 3. And then now if we're going to rewrite this, 6 to the third equals 216. All right. This one tends to be a little bit trickier for people. So let's just do a couple more of these. My base of my exponent is a fourth, so the base of my log will be 1/4. Okay. To the power of -1 equals what's next to. So 4's got to be what's next to, and then -1 has to be what's over there. 1/4 to the -1 is equal to 4, and that is true. All right, so you can try these out. I'll put them here, and you can pause the video. I will put the answers here just so that I can talk about them. But what you should end up with is log base 8 of 4 is equal to 2/3. And yes, 8 to the 2/3 is equal to 4. So then these are, this is also accurate here. 50 to the 0 is equal to 1. Well, anything to the power of 0 is equal to 1. If we were going to write that, logs always have to have a base. The base of a log in this case is 50 of 1 is equal to 0. Okay. So these tend to be a little bit more challenging, going from exponential form to log form. But hopefully this pattern is slowly starting to make some sense here, because this is how we're ultimately going to be using them to find inverses and here to evaluate logs. Okay, so how we do that is we're going to do exactly what we did earlier, put an exponential form, and then we're going to figure out what this exponent is. For our purposes, these will work out pretty nicely. Okay. So what do I mean by that is when you take a look at number 1, log base 4 of 64 equals something. I think it's helpful if you write that, equals x. Okay. So when we rewrite it in exponential form, it looks a little bit more familiar. So how do we rewrite this in exponential form? I have log base 4 of 64 equals x. So you're going to rewrite it. You take your base. Well, my base is 4 to the power of what's over here, which is x, equals what's next to, which in this case is 64. So 4 to the power of something is equal to 64. And now this is kind of where, if you have that power card that was given to you last unit, or if you could just kind of use number sense, 4 to something is equal to 64. Well, 4 to the third is 64, because 4 times 4 times 4 gets you 64. All right, so let's try another example here. This thing is equal to x, so let's rewrite it in log form, or excuse me, rewrite it in exponential form. So since my base of my log is 1/5, the base of my exponent is 1/5, to the power of what's over here is equal to 125. Don't be confused by this with the fraction and the exponent. All right, if you see a 5 and a 125, 5 to the third power is 125. 5 times 5 times 5 gets you 125. But since this is a more of a fraction and the 5 is in the denominator, okay, if you make this a negative 3, then it'll become a positive 3 in the numerator, so then 5 to that positive 3 in the numerator gets you 125. All right. Let's just do a couple more of these so that you get the hang of it. Remember, equals x. That's how I'm going to start both of these. And now the process is similar. You take your base to the power of what's over here equals what's next to. And 2 to the 5th is 32. Similarly, 8 to the x is equal to 1 over 512. And for similar logic as the one right above it, since 8 to the 3rd is 512, 8 to the negative 3rd would be 1 over 512. So that is how you will use the relationship that I started earlier on the previous page to solve for exponents, or evaluate logs. Okay. Now I did tell you that what you will always have with logs is you will always have a base. Okay. Common log is just written as log. So usually there's some number down here, like log base what? Log base 7, log base 12, log base negative 2. But if there is nothing written, then what we assume is that is a log with base 10. So we will never actually see this, because log base 10, you can just kind of assume that the 10 is there if it's just a log. So if you take a look at your graphing calculators, on your graphing calculators, there's a button right next to the 7 here. It's log. Okay, so this is assuming you're using log base 10, because it's just a log. Okay. And then similarly, we have natural log, which we label ln. I know you maybe think that should be NL for natural log, but it's not. And in the language that this was established in, the L and the N are flipped. If you know anything about other languages, then you can realize what they do with adjectives and nouns and all that stuff. But that's not really for here and for now. But we need to realize is that the natural log is a log with base e. So you will not see log base e. You will see ln. Okay, these are interchangeable. Log base e and ln, those are interchangeable. And so this is also on your calculator next to the 4 here, ln, log base e. Because these are used so frequently, okay, base 10 and base e, they kind of have their shorthand for that. So as we get used to ln, I might write log base e just so that you can get used to it. But you will never actually see log base e because that is ln. Right. And your calculator can do these pretty easily. All right, log of 20, that's just log of 20. All right, log of 20 is 1.3. Okay. Natural log of 1/5, well, 1/5 is 0.2. Natural log of 0.2 is negative 1.6. Okay, so you can just punch those in on your calculator. You know, really what this says is what we did earlier, right? You can rewrite this to be log base 10 of 20 is equal to x. So you're looking 10 to some power is equal to 20. Well, 10 to the first is 10. 10 to the second is already 100. So it had to be somewhere between 1 and 2. So 1.3 is where we landed. Okay, so hopefully you can kind CY 1.3 would be the answer there. Okay. All right, very good. Now, lastly, we are going to apply some basic log properties, and I'm going to get into this a little bit more in the next video. This is kind of just scratching the surface of what we're going to be doing. The main point that I want to emphasize is right here, is that exponential functions and log functions undo each other. All right, so just like multiplication and division undo each other, exponentials and logs undo each other. So when you're solving and you have an exponential, if you want to get rid of that exponential, there better be a log, and vice versa. All right. So these log base b and b would just cancel out, and all you have left is x. These would cancel out, and all you have left is x. So when you take a look at number 1, log base b of this of this 3 to the 4x minus 1, these cancel out because the bases are the same. So since these cancel out, all you're left with is 4x minus 1, and you can't do anything more with that. All right. Next one over here, this e and this natural log, they cancel out, because what is natural log? Natural log is log base e. So you have an e to the power of a log, so you have an exponent and you have a log. Those are going to cancel each other out. This 4 actually drops down with multiplication, and 2 times 4 is 8. Okay. Here, since here's a log of 33, it doesn't have a base, so you assume the base is a 10. So since it's 10 to the power of log base 10, those cancel out. All you're left with is 33. And then similarly, ln and e cancel out. All you're left with is x squared. So kind of getting at the inverse relationships of those. And we're going to look at more inverse relationships of those next time. All right. So hopefully this went well. And yeah, thanks for listening.